Hello, everyone. So today we're going to be talking about heat and endo and exothermic things and such. So the reason why we're going over this today, we're going to take some notes and feel free to write down whatever you want. Um, we are just doing notes today for Tuesday. Okay. Wednesday, you will have practice problems in which you have to try some of this stuff out. So you can watch the notes today. You do the practice problems tomorrow. You can do all of this tomorrow. It's kind of up to you, but we are taking notes today. So, all right. Um, Physical versus chemical changes. We're going to talk about these in terms of heat. Okay. We know that with physical changes, remember, physical changes is where you're going to have the same substance when the reaction is over. Like you don't change something into something brand new. So basically, like when you boil water, or when you have a liquid that goes from a solid to a liquid, or when you have a solid go to a liquid state, a phase change, those are all physical changes. We know that heat will travel from areas of high to low. So from areas of hot to cold, heat travels in that direction. Heat changes form constantly. Energy changes form constantly. You're never going to lose it, right? Law of conservation of energy. Okay, when you think about ice melting, would you consider ice melting to be endo or exothermic? When ice melts, when it goes from a solid to a liquid form, would you consider that to be endo or exothermic? Well, and think about the particles of ice on a molecular level. In order for them to go from a solid state to a liquid state, they have to start moving a lot faster. So if you're going to make things move faster, you're going to have to bring in heat. Okay. So the outside, the surroundings are hotter than the inside of the ice. So you're going to have heat traveling into the ice. And so it's going to speed those particles up. They're going to absorb energy. So that would be a very endothermic reaction. When ice melts, that's considered very endothermic. Heat travels in, speeds up the particles, and they melt. Well, chemical changes can also occur, and you can have endo or exothermic reactions. Last week, whenever we took that metal and we dropped it into cold water, we were looking at a physical change, and we were looking at how heat traveled from the metal to the water. This week, we're going to start talking about chemical changes, and just know the energy comes from the bonds within the compounds. Okay, that's where stored energy is. If you look at this little kind of story here at the bottom in the yellow, we're talking about when you start with reactants or the starting substances, all of that energy that's there is stored within the bonds, and we call it stored energy, potential energy. Whenever the reactants start to change, they have to have activation energy to get the reaction started. The bonds will break, the molecules move around, and they rearrange. And of course, we know that to be kinetic energy, right? Once the substances start to move around and they start to reform, new bonds form. And again, you're going to have storage of energy, which is potential energy. If you have leftover energy at that point, if you have leftover or excess energy, that gets released as thermal energy at the end of the reaction. And we would call that exothermic. It feels hot. If the reaction, if the products, if the reactants, the starting substances required more energy at the beginning to break those bonds, and the products would have more stored up energy in the end, then we're going to call that endothermic. If the products have more energy at the end that's stored within the molecules, you call that endothermic, and the reaction would feel cold. Okay, endothermic reactions, guys, you're going to need to know this graph. You have got to be able to recognize this graph as being endothermic, okay? See up there where the product side is, that it is higher in energy than the reactants. You need to write that down in your notes. Where it says delta H, we're going to get back to that delta H here in a minute, but that's greater than 0. If you have a delta H or an enthalpy change of a number bigger than 0, we're going to call that an endothermic reaction. With endothermic reactions, basically, if you have heat on the left side of the arrow. So heat is taken in as one of the reactants. We're going to call that an endothermic reaction. Heat is taken in. You would see it on the reactant side. Okay, endothermic. On exothermic reactions, it's just the opposite. Everything's opposite. Products end up with lower energy than the reactants started with. They have a release of energy. The enthalpy, the delta H there, is going to be less than zero. So in other words, delta H is going to be a negative number. And this is a reaction in which energy is released by matter. Down here at the bottom, it says A plus B yields P for product there. I'm not sure, why they didn't use something else or like AB, but plus heat, you would see heat being produced as a product. Like it would say plus and then give you a number of kilojoules. And again, delta H would be a negative value, just like Q. Q would be a negative value. So, all right. So take a look at this. You've got this problem. NaOH, that's sodium hydroxide and hydrochloric acid, HCl, yields water and salt, NaCl, plus 57.9 kilojoules per mole. Would you consider this endothermic or exothermic? Well, look at where the number is. See where that 57.9 kilojoules per mole is? It lands on the product side. So heat is produced as a product. So would you consider that endo or exothermic? Exothermic. If you guessed exothermic, you did it right. Okay, all because that number shows up as a product. It's energy that's being released out as a product, so the reaction would feel hot. Here you have ammonium nitrate. Oh, they left off something. Anyways, you have ammonium NH4 and then NO. I feel like that's written wrong. I would need to go back and check that. Anyways, plus what we're looking at though is the number there, 3650.9 kilojoules per mole. It's on the left side of the equation. It's a reactant. It has to be there as a starting substance. You have to have energy to start the reaction. So is that considered endo or exothermic? Endothermic. If you see the number, if you see the kilojoules on the left side of the equation, it's going to be endothermic. Okay, so let's do this problem. The combustion reaction of propane described by the equation below has an enthalpy change of negative 2,044 kilojoules. What would the enthalpy of the reaction be of 0.25 moles of propane and 1.25 moles of oxygen? At this point, guys, if you need to pause the video and write this reaction down, like the C3H8 part, go ahead and pause it and write that down. And I'm going to switch over. Hopefully, I'm going to switch screens here in just a second. Okay. So here's what we've got here. Let's see, where's my calculator? Okay, so there's my propane. That's C3H8 plus 5O2. All right, and they're saying with this reaction right here, if you have propane with 5 times the amount of oxygen you would need in order to get this to combust, it's going to produce carbon dioxide and water. And, of course, since this is a combustion reaction, this is fuel mixed with oxygen, it's going to produce a lot of energy, right? Negative 2044 kilojoules for this reaction. That's the change in the heat of the reaction. Negative 2044 kilojoules. Okay? So that is associated with 1 mole to 5 moles. That's the ratio. But now they're saying, well, what if you had, though, only 0.25 moles with 1.25 moles of O2? And by the way, this is the correct ratio. If this is 1 to 5, if you had 0.25 of this, you'd have 5 times as much, which, ta-da, is really 1.25. So we can use either one of these to check out our ratio. So here's how we would set this up. If we know that you have for every 1 mole of propane, it has to, or it will produce negative 2,044 kilojoules of heat. 1 mole will produce this much heat. We can set it equal to what we know about this new information. What if you only had 1/4 of a mole of propane? And we want to know how many kilojoules would that be? how much energy would be produced from there. So all I did was I set up a direct proportion ratio. This is what I know from the equation. I'm going to set it equal to my new information. And then at this point, all we'd have to do is cross multiply and solve for x. So I know then that 1x equals just a quarter of negative 2044, right? So I'm going to do negative 2044 times 0.25, oops. And I end up with negative 511. And what that means is for every quarter of a mole of propane that you use, it's only going to produce a quarter of the energy, right? A smaller amount of energy, which makes sense. Okay, so there's one type of problem that you might see on the homework tomorrow. Okay, it's a smidgen of stoichiometry. I know I told you that we'd be done with that, but sometimes it just pops back up, guys. All right, let's keep going. So there's one type of problem that you're going to encounter. Enthalpy, let's talk about this word. It's fun to say. Try it out. Enthalpy. Delta H is the amount of energy transferred in a system as heat. It's the heat of the reaction. So when I ask you calculate the enthalpy of the system, I'm just asking you about how much heat was either needed or produced in the reaction. Okay, there is this weird looking formula, and we're going to go through this here in just a second, but basically what it says is that the delta H, so the change in the heat of the reaction or the change in enthalpy, is equal to, it's got that weird little E looking thing. That is a sigma, okay? It's a Greek letter, sigma. It just means it's the sum of the moles or the coefficients times the enthalpy of the products minus the sum of the moles of the enthalpy of the reactants, which sounds really, really hard to do, but I promise this is not going to be difficult at all. I promise. So what you need to keep in mind, though, is that if delta H is bigger than 0, if it's a number greater than 0, or if it's a positive number, it's endothermic. It means it's an endothermic reaction. If delta H ends up being less than or a negative number, it's exothermic. All right, so let's go back to here. Oh, wait, I forgot. Hold on. Okay, so take a look at this. Maybe. There it goes. Okay. Here's this problem. It says the combustion of methane produces carbon dioxide and water. Calculate the delta H for the equation and classify the reaction as endo or exothermic. I promise you will have a problem just like this on the homework tomorrow. Okay? So, if you're taking a look at this, I encourage you to write the reaction down. We're going to be looking for delta H, right? And so, let's go ahead and get some other information here. I want to show you this. This little table here basically tells you the amount of energy that's produced from the formation of these molecules, okay? So this is bond energy, basically. It's the energy that's stored within the molecule. So what we're going to have to keep in mind is when we're doing this problem is how much bond energy is available for each one of these things. So here's what I would like for you to do. Write down the equation. The CH4 plus 2O2 yields CO2 plus 2H2O. Then go up and find the CH4 in the chart. Can you find it? How much energy is produced from that molecule? And it says negative 74. So on my paper, and I'll show you this in a minute, I'm going to write down negative 74 right underneath the CH4. Okay? So the next thing that comes along in the equation, it says is 2O2. Well, if you'll notice in this chart, there is no just oxygen. There's no O2 molecules. So what do we do about that? Well, just know that the enthalpy for O2, it's 0. All of the enthalpies for your diatomic elements are always 0. There is no bond energy there. So So I'm just going to put, like, I'm going to record on my paper here, right underneath where I had 202. I'm going to say it's 0. There's 0 kilojoules of energy there. Okay. Then if you move to the next part of the equation, the product side, I want to go find CO2 gas. Can you find that in the chart? It says it's negative 394 kilojoules per mole. And then you've got liquid water. Okay, and if you find that in the chart, it says it's negative 286. So I'm going to go ahead and write that down. Okay, I'm going to switch back over now to the ladybug here so we can look at this together and show you what I've got written down. Okay, here's what I've written down so far. So there's my equation that I just copied down from the problem. Here are the values that I copied down from the chart, and I just wrote them underneath. And here's the next thing I'm going to do. I'm going to go back and look at, this is my enthalpy formula. This is going to help me calculate my delta H. And remember, this means the sum of the moles. So I'm going to go ahead and label this, that this means sum, or I'm going to add up, right? So I'm going to add all of the product's enthalpy values, all of the enthalpy values. This number right here just indicates that this is going to be the coefficients, or the amount of moles, which is just to say, basically, if there's a coefficient, you're going to have to multiply the coefficient times the enthalpy value before you can go and add it in. Okay, so since we're going to do the product side first, down here, I'm going to put delta H equals, and I'm going to focus on my product side first. Okay, so I'm going to put parentheses up. This is negative 394 plus, because it's the sum, right? And here it says we have negative 286 for 1 molecule of water, or 1 mole of water. But see, remember how we said if you've got coefficients, you're going to have to multiply? So I'm going to go ahead and do 2 times negative 286 so I can see what to put here. And it's negative 572. So this is my product side. And all I've done is I've taken the enthalpies that came from the chart and I'm plugging them in and I'm going to add them up. Okay. If you have a coefficient, you got to make sure and multiply by the coefficient. Okay. Now, products, you're going to take the sum of the products minus the sum of the reactants. So minus, I'm going to do my reactant side now. So now I'm going to look just at the reactants, the starting substances. Okay. So this is going to be easy, right? You just got negative 74 plus 2 times 0, which is 0, right? Okay, now comes the part of the show where we're going to just add all of this stuff together. Okay, so negative 394 plus a negative 572. So negative 572 plus negative 394. So we got negative 966. And then negative 74, so that's going to make that a positive 74. Okay. And that's going to be, so negative 966 plus 74. You end up with negative 892. And so what does that mean? Negative 892 what? That's how many kilojoules were produced in this reaction. That's the change in the heat of the reaction. That's the delta H. That's the change in the heat of the reaction. Delta H is negative 892 kilojoules. So basically, when you combust methane and it goes through this reaction and produces carbon dioxide and water, there's heat left over. Like there was, whenever these products are formed, they're stable enough. It's that there's going to be excess heat and excess energy left over whenever these products start to form. So whenever you have heat left over, Would you consider this to be an endo or an exothermic reaction since it's a negative enthalpy? Well, if you look back at the notes, we said if it's a negative number, it's going to be exothermic. And guys, it's combustion, right? This is fuel and oxygen. Combustion reactions are always exothermic, so they're going to produce heat, right? Okay, so let's go back to here. Okay, and let's keep going. Okay, on this particular problem, it says find the standard enthalpy change of the following reactions. There you've got ammonium nitrate, solid ammonium nitrate that breaks down to form N2O, so dinitrogen monoxide plus liquid water. Okay, so we can write this reaction down. And so take a minute and write that reaction down. And go ahead and do like we did a while ago. Label the products and the reactants with the correct enthalpy values. And that delta HF just means the enthalpy of formation. So we're going to do, for the NH4NO3, I'm going to put negative 365.6. And then for my N2O, I've got 82.05. And then negative 285.8. Okay. And we're going to try to come up with the delta H. All right. So let's go back over here. All right. That's what I got so far. Did you guys write down the same thing? Okay. So before we do anything else, let's remember what our formula is. If you're going to calculate delta H, we're going to have the sum of the moles of the change in the enthalpies. So moles times the change in the enthalpies. So remember, this just basically means coefficients times the delta H of the products come first minus, we're going to do the same thing for the reactant side. So the sum of the moles times the delta H of the reactants, right? We know that. So now let's start plugging stuff in. We're going to have delta H. Let's do the product side first. Let's do this side. Okay, so I'm going to take 82.05 plus, because we're summing it, we're adding it, right? And remember, look, you got to look for coefficients. I got a coefficient right there, so I'm going to multiply 2 times negative 285.8, and I end up with negative 571.6. And I'm going to put that right here, negative 571.6. Minus, I'm going to go get my reactant side, minus the sum of the coefficient times the reactants, which is just negative 365.6. Okay, so here we go. We're just going to do the math here. So I've still got my negative 571 in there. So I'm just going to add to that positive 82.05. So I end up with negative 489.55. Okay, negative times negative, right? So we got a positive 365.6. We'll do that. Okay, so I'm just going to add 365.6, end up with negative 123.95 kilojoules. That's the delta H of formation. That's what it took to form these products. So again, if you have a negative amount of energy that's produced, negative doesn't mean that you have a decrease in value. It indicates direction. It's trying to tell you what happened to heat flow. Was heat going into the system or out of the system? Well, if it's negative, it means it's flowing out. It's exothermic. You have a change in the heat of the reaction, and it ends up being exothermic. Okay? Good enough? Yeah, Miss Lovell, I got it. Good job. All right. I feel like, yep, that's it. Now, if you're super interested in this topic and you want to take Chem 2, we'll talk about Hess's Law next year. That'll be one more thing we add on. But anyways, other than that, that's it. You'll have some practice problems over this tomorrow. I hope you understood this. And if not, you can always email me. All right.